So, our second part here is all about centripetal forces. Centripetal force is the force required to keep an object traveling in uniform circular motion. So if you can imagine a ball tied to a string and someone's twirling the ball in a circle, the centripetal force in this situation is coming from the string, so it would be a tension force. Centripetal force, once again, means center seeking, as mentioned before. So a center-seeking force, this is the force that pulls the object towards the center. And it says look at 5.1.4, the acceleration points inward, so we'll look at this in this situation here. And number 3, centrifugal force with an F. That is a center-fleeing force. These forces are... This says false, but I almost want to think, I also like the word fake for this, just about. Because when you feel like you're feeling a centrifugal force, it's not really there. And that occurs because you're in a system that isn't an inertial reference frame. So as an example of a scenario where you might feel a centrifugal force. When someone's driving a car, they're going fast, and they turn really quickly around a corner. You might feel like you're being pulled towards the outside of the car, but there is no force doing the pulling there. The issue is that you're comparing your motion to the car, which is accelerating. Your actual reference frame is accelerating, so there's no force there. The force you're kind of fake feeling is your momentum pulling you into the side of the car. So just keep in mind, centrifugal forces, they aren't a real force as we come to know them. So looking at an example, driving a car. When we're looking at driving a car and going on a corner, friction is the force that's causing the car to turn. It's providing the centripetal force. As the car turns, your inertia wants to go straight, and the car turns underneath you. The car door is and when you do that, the car door is hitting you. You are not being pulled outward towards the door. And then Mr. Osblinski has a little picture here where your velocity is trying to go this way. It's trying to go tangent to your curve, but the friction force is providing a force in here like this. I'm just going to call that centripetal. And I want to say one more thing about centripetal forces. When you make a free body diagram and you try to draw something like this, there isn't, like, you're not going to point to something and say, ooh, that's a centripetal force. Because you won't necessarily, like, it's not like a friction or a tension force where you know what's there. Really, a centripetal force is just a friction, a tension applied, any kind of force that just happens to keep on pulling towards the center. So in a way, centripetal forces often act like net forces. So this last little bit here, when we're looking at a centripetal force, because we're deriving this from Newton's second law, so sigma F equals ma, when we're looking at a uniform circular motion, we know that the acceleration, the centripetal acceleration, is simply just v squared over r. So we do get this little shorthand equation here where we essentially get mv squared over r is equal to the centripetal force. So we'll be using that equation from time to time as well. So as we continue downwards here, excuse me, we're being asked to look at the common scenarios that can happen and try to pre-solve them with equations, which might help you later on too. So in this situation, we have a little loop. You can imagine a little car traveling on this thing like a Matchbox car or something. And it's going to go up this side. And then out the other side. Okay? So the scenarios you might see a lot of will be the top, the bottom, and then if we're trying to make it so you feel weightless at the top. So let's start at the top first. Okay, if we're moving at a constant velocity, we don't have to worry about anything going on in the x direction here. So the forces that we're going to have in play will be the mg from the car, but because the surface is above the car, we'll also have a normal force pulling downwards. So when we take a look at our sigma f equation, which we do know is going to be MAC. This sigma f piece here, we can replace it with a negative Fn minus mg, because both these forces are pulling downwards. And that'll be equal to m, and we can make the replacement now of v squared over r. What I want to point out is that because this thing is accelerating towards the center of the circle, this acceleration here is technically negative, so that will be negative as well. So if we do a little step here where we add mg to both sides, we get mg minus mv squared over r. And then if we just multiply both sides by negative 1, we do wind up with the equation mv squared over r minus mg. So this equation, you can use it whenever you're looking at an object going through essentially the loop, as long as it's talking about the top. On the bottom, the scenario changes a little bit. Normal force will be going upwards, and the mg will be going downwards. Just as last time, we'll start with our sigma f equals MAC equation. Helps that. And this time when we plug in sigma f, that becomes Fn is going up, it's positive, minus mg, and that'll be equal to mv squared over r, which stays positive this time because of the fact that the acceleration is going towards the circle, the center of the circle, which is upwards, so that works out. In this scenario, we add mg to both sides, and we get Fn equals mv squared plus mg. So that equation will be good for any time you're looking at the bottom of a loop. Now, occasionally, a problem will ask you, how is it possible to feel weightless at the top of your curve, of your loop? And when you feel weightless, it means that your normal force is equal to 0. So all we need to do is just kind of take this equation up here, and essentially just drag it down and replace Fn with 0. So if we do that, we get 0 equals mv squared over r minus mg. If I add mg to both sides, I get mg equals mv squared over r. And right off the bat here, we do see the masses can cancel. Now, in these kinds of problems, we're usually going to try to solve for the velocity. So let's just solve this thing for velocity, and then we'll have a pretty good equation to use. So if I multiply both sides by r, we get rg equals v squared. And then getting rid of the square, we move both sides to eventually find v equals root rg. That equation will work whenever you're looking for the weightless velocity, or what velocity causes weightlessness at the top of the loop. All right. Let's go back a little further. Let's continue and look at an unbanked turn. If we're looking at an unbanked turn, we're going to imagine that this vehicle is driving towards us. So, sorry for drawing this horrible excuse for a car. Looks kind of angry. The forces at work on this car will be the normal force going upwards, the mg going downwards, and we have a friction force pulling towards the center. Okay? Because the circle is in the x direction and the circle is kind of like, the center of the circle is this way and the circle is coming like this, it means that our sigma f direction, the x direction, that will be where we get our centripetal acceleration. And over here, on the y direction, that'll just be equal to may. That's just normal. And over here, we can plug in, the Fn should be going upwards, mg down, and that'll be equal to may. But we do know ay should be 0 in this scenario because the car should not be getting airborne. So we do wind up with Fn equals mg. That should feel somewhat similar to Unit 4 with forces. All right. The x direction is where we get our new stuff. So starting things off over here, sigma f, that's just going to be equal to FFR. And over here, AC, we can replace that with a v squared over r business again from that equation we learned a little bit ago. And if we start doing some substitutions, because we know friction force equals mu Fn, we can replace this side with mu, and we know Fn is equal to mg. So I can replace it with umg equals mv squared over r. And notice here we have m's on both sides, so they do cancel. And we get mu g equals v squared over r. If I multiply both sides by r, I can solve this for v, which might be a helpful equation to have. So we do wind up with r on this side, and this r cancels, and we get mu g equals v squared. And if I root both sides, we do get our final answer of v equals root mu rg for this scenario. Our final scenario is going to look at a banked turn, and we'll take a look at that in the next video down. So just click on the next one, and you can continue through the lecture.